Good evening, Bearcats. Tonight we're going to talk about our 1.2 graphs of functions, and we're going to talk about the different topics within that. I really want you working on your 3-column notes. I've done some outlining here for you, so you can just copy this down, pause as often as you need to get this copied down. So let's go ahead and keep going here. So we're going to talk about forms of linear equations. We're going to focus this year on our point slope form, and I want you to write those forms based on your prior knowledge. We're going to talk a little bit about quadratics in this case, and again here are 3 versions of the quadratic, and again I want you to write your quadratic based on this information. Your absolute value function, again, writing the standard form based on the given equation. So the right-hand column is the stuff that you need to do, but you need to write all of it down. So you need to have the picture, you need to have the equations, and then you need to do the work on the 3rd column. There's equation of a circle, same thing. And then we're going to talk about special functions in detail and kind of do that part together. So you're going to want to pause and go ahead and catch up with me to this point, and then we're going to do special functions together. We're going to stop there and go on to a couple of examples that will help you with your pre-assessment tomorrow in class, and then we'll pick back up the last couple of concepts on this tomorrow night. So you go ahead and pause and get ready and catch up, and then we'll do special functions together. Okay, our special functions that we're going to discuss, and there are several other functions, and we're going to actually add one that's not even on this list and talk about as well. But the first function we're going to talk about is the square root function. So this special function would be your square root. Your square root function. Let's talk a little bit about the properties of a square root function. We're going to go back and talk about that after we actually see the graph. We're going to go over here and sketch our graph next. And I'm going to just create a little t-table. You may remember what this graph looks like already, but I always can fall back on a t-table for my x and y values just to figure that out. So remember, I'm actually substituting into this parent function, or this base function over here. So if I pick, the other thing we remember is that I'm sure that you all remember that a square root, that you have to have, you can only have 0 or greater. You cannot have a negative under a square root. You can have 0, but you can't have a negative. So we're going to start with 0, and the square root of 0 would be 0. Next we'll be choose 1. The square root of 1 would be 1. And then we're going to pick carefully to make it easy on ourselves. So I'm going to pick 4 because the square root of 4 would be 2. And there's a few points for us to start sketching our graph. So we would start at 0, 0. We would have a point at 1, 1. And then we would have a point out here at 4, 2. And our graph would look something like that. Something like that. So I want to talk a little bit about the properties of this graph. Our domain and our range, both, I'm going to write it all out, are all non-negative real numbers. So all non-negative real numbers. So that domain would be really, and the range would both be 0 to positive infinity. And so 0 to positive infinity, and 0, we could have a 0, and infinity would get a soft bracket. The intercept of this graph is at 0, 0. So our intercept is at 0, 0. That's our y and our x intercept. And then let's talk a little bit about something called which interval it is increasing or decreasing. And we would say in this graph, and I think this is really important, this is a little bit more the pre-cal versus the algebra 2 part, is that we're going to say that we're increasing on the interval from 0 to positive infinity. And intervals are just soft brackets. But on the interval of 0 to positive infinity, the graph, as you move from left to right, the graph is moving upward. That's kind of visually how you would look at that. All right, let's take a look now at the cube root function. That would be your next one. So you have a cube root function. Let's take a look at what it would look like. Again, I'm just going to use that little t-table. I'm going to go through now, you kind of understand. Now a cube root, an odd root, can have a negative because a negative cubed would be negative, and a negative positive cube would be positive, so you can have both. So that's why. So you can have positive and negative values. I'm just going to fill in my chart real quick. So if you had 0, 0, the cube root of 0 would be 0. The cube root of 1 would be 1. But the cube root of negative 1 would be negative 1, because negative times negative would yield a negative. So for odd roots, you can have negative values. For even roots, you cannot. Let's go ahead next and pick something carefully. So we would pick maybe 8, because the cube root of 8 would be 2, and the cube root of negative 8 would be negative 2. And that's probably good enough. And I'm just going to sketch. It's going to be a little hard. This is a small graph, but you'll be at 0, 0, of course, 1, 1, and then 1, negative 1, negative 1. Then you'd be all the way out at 8, 2, and all the way out here at 8, negative 2. And your graph would look something like this. And you should know this from Algebra 2, but I'm just jogging your memory again. Again, here, the domain and the range would both be negative to positive infinity, be all real numbers. So we're going to write an interval notation as negative to positive infinity. The intercept, of course, is at 0, 0 again, and that would be both your x and y intercept in this particular graph. And then again, now this is interesting, because it looks like if you're not careful, you're looking at this graph and you think, oh, it goes down on the left. Well, it does, but when we're talking about increasing and decreasing, we're reading from left to right, just like when you read words. So we're moving across the graph this direction. As you move across this graph this direction, the graph is increasing. So this is also increasing on the interval, and this time from negative to positive infinity. All right, let's move down just a little bit more, and let's take a look at the the y squared equals x. We're used to seeing y equals x squared, but this is the y squared. Well, first of all, let's just take a little look at what our t-table would yield. All right, so I'm going to go ahead and plug into y because it's a little easier for me to do, so be really careful with that. So if I plug in a 0 and I square it, I would get a 0 for my x value. If I plug in a 1 for y and I square it, I would get a 1. If I plugged in a negative 1 for my y value, if y was negative 1, my x value would be positive 1. If I plug in a 2, I would get a 4, and if I plug in a negative 2, I would also get a 4. So let's just graph those ordered pairs. You understand when you create this t-table, you've created a set of ordered pairs. So we have 0, 0, we have 1, 1, we have 1, negative 1. We have 4, 2, and we have 4, negative 2. All right, so I am going to draw my little graph. This is actually a conic section. It is not, and hopefully you remember this is not a function because it does not pass the vertical line test. So if I had a line going across my graph, it would be hitting 2 places at one time. Very quick visual to check for functions or not. So this is not a function. All right. Last, I'm going to squeeze in here the greatest integer function, and that is written as y equals. And it's going to be written kind of these little funny brackets. It's at the bottom with it looks like an L and kind of a backward L, and that's called the greatest integer function. All right, and I'm going to have a really hard time kind of squeezing this little graph in. You may or may not have been introduced to this in Algebra 2. I think you were, though, but it's like a step function. It looks like stair steps. So the greatest integer is the greatest integer that is less than, okay? So less than. And they have to be integers, so they can't be whole, they can't be fractional parts. So you're going to start here, and you move over 1, and you have an open dot. And then it steps up to 2 and over, and it steps up and over. And your function looks something like that. When we go down, we're going to go down, and you'll have an open dot, and of course closed, and down, open dot, and closed. We'll talk a little bit more about this function in class tomorrow. I want to discuss this a little bit more with you, but that's just a visual for you. Those are some really important functions. All right, I want you to stop in your 3-column notes after this tonight, and we're going to go on and do a couple of examples for tomorrow's pre-assessment. But tomorrow night we will pick back up with rational expressions and symmetry. So go ahead and pause and catch up with me, and then we're going to go on to our 2 practice problems for tomorrow. Okay, tomorrow in class you're going to do the second part of your pre-assessment. We're just determining all the skills that you have learned from last year. We're trying to review those quickly so we can move on into our pre-cal part of things. You have 11 problems tomorrow, and I'm going to work 2 of those 11 problems. The first problem I'm going to work on is problem number 5. Oops. Well, can't get that paper out. Okay, well, we'll just start here. Problem number 5. Problem number 5 is going to be a vertical motion problem. And there's a couple of formulas that you learned last year that we're going to kind of review. So I'm going to review the 2. If the problem is discussing feet, then your equation for vertical motion is, which is your height and time, height over time problem, is your height is equal to negative 16 t squared plus vt plus s. And if we're dealing with meters, your height is equal to negative 4.9 t squared plus vt plus s. And a couple of things that you need to remember, that t represents time, h is the height above the ground at a particular time. S was our starting height, or our initial height, where the where the object began. And then v is our velocity. And our velocity will be positive if something is projected upward. It will be negative if it's projected downward. And then it would be 0 if it was just dropped. Now, that's not quite true if you're in a higher level physics class, because there would be gravity and all sorts of things, but that's what we're going to use in this class for vertical motion. All right, so when you look tomorrow about vertical motion, about this particular problem, you're going to see that this is about a rock being thrown downward. Ooh, downward, so my velocity will be negative. It's going to be thrown downward from the top of a building, a 500-foot building. So it's going to start at 500 feet, so my S value will be 500. It's going to have the initial velocity of 47 feet per second, but it was negative. So negative 47 for my velocity. That's really important because of it's being projected downward. It wants to know how long, so that means we're not going to know the value of t. After the rock is thrown, is the rock 375 feet from the ground? So they want to know the height above the ground after time has passed, and they want to know when that height is 375 feet. So we've kind of written everything down. We're going to fill it in. So we're going to have 375 equals negative 16t. Remember, we don't know time. We're looking for time in seconds. And we're going to have minus 47t because our velocity is downward. It's being projected downward, and we began at 500 feet. All right, tomorrow we'll put these in our calculator. I'm not going to do that on here, but you'll put that in the calculator. You can do it a couple of ways. You could move the 375 over and set it equal to 0. You can put this in the calculator and the 375 in the calculator and actually get a graph and calculate the intersection points. There's several ways, so we'll talk a little bit about the calculator use tomorrow. What your picture would look like, though, is that we have this building and something is being projected, and the building is 500 feet. And hopefully you have this in your notes, because I'm going to check this tomorrow to make sure. This will be a grade for you to have this written in your notes. And we want to, it's being projected downward, so the object is moving downward. And we want to know when it is, what time it is at 375 feet. So we're going to say from here to here was 375. So we're really looking for that point right there if we're looking at it graphically. And since we want time, across the bottom our x value equals time, and our y value, of course, is the height. And so this is an x and y ordered pair at this point. And basically the height we already know is 375. We want to know the x value, or the value of, which would give us the time in seconds for this problem. So hopefully that's a little bit of a review for you. All right, pause, write down what you need to know, and then we're going to do one more problem and we're done for tonight, Bearcats. Okay, we're working on rate and time problems right now, and this is one of those problems where something happens in a total amount of time. So you do one thing plus another thing, and it happens in a total amount of time, and you're trying to determine a rate or a distance. And in this case, we're going to determine the rate. This is about swimming upstream and downstream. You've had these problems in before in Algebra 2, and so we're just trying to review them. This particular problem starts with Mark, and he swam upstream 100 meters, and then he swam backstream to his starting point. So up and then back. So that's a total trip. And the current was flowing at a 1 meter per second. It took him 80 seconds, so his time was 80 seconds to make the round trip. We want to know what his rate was. How fast was he swimming? Well, let's set up this problem, how we're going to do this. So we're going to have our distance over our rate going upstream, so this is going to go up, plus the distance over the rate going downstream, and that equaled a total time. And let's plug in what we know. We know that his distance was 100 meters, both times, and we know it took him 80 seconds to make the round trip. So we've got that already, and his current was running at meters per second, 1 meter per second. So going upstream, he swam his rate, but going against the current, when you're going upstream, the current is pushing against you at 1 meter per second. So we're going to say minus 1. Then he turned around and he swam downstream. He swam at the same constant rate. His body was moving his same rate, or not his body, but his arms were, I guess, moving at the same speed or intensity, but his whole body in the water was moving faster because the current was going with him, flowing with him at 1 meter per second. So we're going to say plus 1. This becomes a rational expression, and hopefully you remember how to solve these. We're going to do this as an algebra review. Once we get to a quadratic, once we get to a certain point, we will go ahead and use our calculator to finish solving it. So rational expressions, I'm going to make this all fractions. If we're going to do anything with fractions, we have to have common denominators. So our common denominator, of course, would be the r minus 1 times the r plus 1. So r minus 1, r plus 1. That'd be our common denominator. When we look up here, this has r minus 1, so we would need to multiply the top. Since we already multiplied the bottom by r plus 1, we'd need to multiply the top by r plus 1. Over here, we have the r plus 1, so we need to multiply the top and the bottom by r minus 1. We already did it down here in the bottom. And over here, we just have a 1, so 80 is going to get multiplied by both r minus 1 and r plus 1. All right, well, you're in pre-AP, so I'm assuming that you can make all those calculations, do your distributing, combine all your like terms. When you do and combine all your like terms, you're going to set it equal to 0. All right, and so what you're going to end up getting here is going to be, and the bottom really won't matter, you're going to get, let's see, 100 r plus 100 plus 100 r minus 100, and then on the other side, you're going to get 80 r squared minus 80. And that's what you're going to get. And then after that, then the bottom really won't be important for us anymore. We had a common denominator. Everything is equal in the bottom. We're going to solve the top of this. Combining like terms, you'll end up with a quadratic, something like 80r squared. I guess this should have been an r. Yeah, oh, that is an r. 80r squared minus 200r minus 80 equals 0. All right, and at that point, I am going to let you just stick it in the calculator, find your intersection points. I'll refresh your memory on the Inspire calculator if you don't already know so tomorrow. So I want you to go ahead and put it in the calculator tomorrow. Why don't you do that tomorrow? And first thing when you walk in the door, pick up the calculator because you're going to be using it. Go to number 10 since you've already written it down and calculate that answer, and then put it in a big circle on your note so that I can take a look at it and give you a grade for doing your work. All right, I hope you have a great night, and I hope you have a good third day of class tomorrow, and I will see you then. Have a great night. Good night, Bearcats.